Hello and welcome back for the second webinar in a special three-part AI for Engineers webinar series brought to you by Design Engineering Magazine. I'm your host for today's discussion and editor of Design Engineering, Sean Terry. AI is radically transforming design and manufacturing through the enhancement of product development, the reduction of costs, and by enabling smarter decision-making. Machine learning and generative algorithms are enabling teams to explore countless design options, predict outcomes with precision, and bring breakthrough ideas to life, reshaping industries and redefining possibilities. During today's session titled AI-Powered CAD, our presenters will explore the ways in which AI-driven design and simulation tools are accelerating innovation within the design and manufacturing space. However, before we get into the content, I'll let everyone know that there will be time once the presentations have concluded to ask questions. If at that time you have a question for one of the presenters, just use the question tab to ask it, and we'll do our best to get to as many as possible. Also, this session is being recorded and will be made available for viewing shortly. Without further ado, our first presenter is Nico Haag, co-founder and director of simulation engineering at PhysicsX, a pioneering deep tech company at the forefront of AI and engineering. Nico joins us today to talk about some of the real-world applications of AI in engineering, demonstrating how these models are being used to improve efficiency, solve complex problems, and drive innovation across industries. Please welcome Nico Haag.
Thanks a lot, Sean. Let me get started and share my slides here. Very quick overview. Thanks for the intro again. Or what we are. We're a team of about, I think, 130 people now across, engineering, data science, and software engineering. All sorts of very diverse backgrounds. I think how we are structured is quite important. So we've got a big delivery team working and closely together with the customer, co-engineering, solving hard problems and high-value problems especially. We've got a big product team as well, and a research team working on the latest and greatest out there. Let me get to the interesting bit. I thought, today we'll tell a little bit about the technology side of things, how we see things developing. I think Theo will also talk about the user side of things and what does it mean for the engineer itself. So very quickly here, I think, everybody knows the timeline a little bit. We, got from physical testing to numerical physics, CAD design, replacing drawings and things like that. In the 19th, earlier than that, and then now the last couple, decade got to machine learning, deep learning, GPU, and so on. I think this is how we started 2020, doing some first use cases there. Then a lot of new architectures since then, and last year we got into foundation models for geometry for physics. I'll get into that a little bit. But I think what's interesting here is speak a little bit about, okay, what's next in terms of AI for geometry, AI for physics, and AI for engineering in general. So what I've done, I've structured it, split it into the physics side, the geometry side, and the more or less holistic process side of things. And, talk a little bit about the trends we see. Please ask questions after. Highly appreciate it. I think the first one is pretty obvious, right? In terms of physics, of course, there are new solvers coming up. GPU accelerated solving, parallelized solving, cloud compute, all of that can speed up your process. I think what's more interesting here is, of course, what we can bring, what also Null Concept is bringing in terms of AI inference, and what we're bringing on and foundation models where, instead of going 5 to 50x in speed up, you can go a magnitudes higher, so 10 to the 4, 10 to the 5 in speed up. You can reduce simulations that take a couple hours or days to seconds. You can iterate and optimize across a high-dimensional design space using these models, which is also a lot cheaper in terms of compute, and do that. And with foundation models, of course, trained on a vast amount and a broad amount of data, also you can create assets for the company and using these models across a wide range of applications while not just limited to a single application, which not always makes sense for specific applications. The last one, of course, coupled to that is holistic system level optimization. As soon as you got an AI model which runs in a second or less, you can explore a high dimensional design space. So, you can explore 500 to a million designs per day on a little GPU. You can parallelize that as well. But what that means is you can easily explore vast design spaces of 50, 100 or more parameters. That means you're not just sticking to, the designs done today on component level, but you can look at whole assemblies and you can look at the full system and optimize across these high dimensional design spaces, which is really the game changer in a lot of industries where you've got complex assemblies. Speaking of that, of course, a lot of that, as soon as you got a simulation that runs, at the accuracy of a CFD of the FEA model, then the bottleneck becomes the CAD side of things, the geometry side of things. And I think what's interesting here in terms of transformative technologies is the representation side of things. Of course, we all know the limitations of CAD systems. We know the plus points around, being able to incorporate all these constraints, all these manufacturing constraints and things like that. But there are also limitations in terms of speed, in terms of design freedom specifically. I think we all tried to run some parameter combinations that crashed the kernel and the model itself. So in this case, I think what's also interesting here is looking at a larger number of different geometry representations. There's, of course, the foundation model side, the large geometry model, how we call it. I'll get to it into a little bit later, based on, sign distance function and things like that. But you also probably have seen, of course, things like explicit and implicit modeling as well as mesh morphing. And I think there's, depending on the application, there's a reason to use all of that, sometimes even in combination. That increased design freedom. The thing is, of course, if you can do a million designs per day, it doesn't matter. You're basically unconstrained in terms of running simulations, creating new geometry. Even if 99.9% is stupid, you still got 100 or 1,000 geometries that somehow make sense, and that are beyond human imagination, beyond what a human come up with. And I think that's the exciting bit. On the other side, of course, you need somebody to constrain that in the first place or after, down select that, and incorporate that into the pipeline, into the workflow. At the second, of course, we're speaking a little bit about foundation models for geometry, generative geometry. That's different to, physics solvers like join methods and things like that, or if we get into topology optimization, this is quite different here, and we'll get into that a little bit, but it's also a good way to mention that here. And of course, here again, this is all about basically having a model that has seen all sorts of geometry, that can come up with any sort of geometry. This enables you to come up with geometries beyond, what a human would come up with, what an engineer would come up with, and just explore everything, right? These models have seen everything, and they can come up with anything. And that's what we're seeing a lot, and that is quite exciting, I think. Last one, of course, which I want to cover is, of course, agents. And what are agents? Agents are basically task-specific large language models. You probably all have used ChatGPT and things like that. These are just models very specifically trained for one thing, that can be manipulating a CAD system, can be manipulating CAE, so engineering physics simulation, that can be AI model, that can be optimization. And what that means, together with the second point, is multi-agent systems, is that you can break complex tasks down, like, designing something, which engineering is usually extremely complex, and we'll get into that a little bit later. You can break this down into, multi-agent problems where multiple agents, you can think of that like multiple people working together to solve a problem based on very specific tasks, broken down in specific goals. I think this is also something that is very relevant across the whole, engineering process, across, okay, how do I do geometry? Is that based CAD? Is it based on morphing? Is it based on large geometry models? to simulation. How can I automate that? A lot of the time is not spent on parallelizing, orchestrating simulation, but setting it up in the first place, getting the meshing right, all of that sort of stuff. It's of course early days with agent, but I think there's a lot where these agents can help you, doing the simple or the manual stuff fully automated and focus on the important stuff like setting up optimization constraints and objectives and things like that, and making sure there's really an optimum design getting out of that may, fits into the problem statement. So that's the other side of things, and I think hopefully that gives you a nice overview, of the trends of the transformative technologies we are seeing across, geometry, physics, and the channel process itself. In terms of, speaking a little bit about very high level about the large geometry models, pre-trained models, the difference is here usually what you're doing is you train a model from scratch. Of course, you need a lot of training data. Depending on the architecture, I think we can get this down using geometric deep learning to 50, 100 simulations, which doesn't sound a lot, especially it's not a lot for data scientists, but it is quite a lot if you think about running 100 CFD simulations or something on external error or things like that. So we want to get this down. One way to do that is having pre-trained models we can use for our customers and in general. We also have Airplane. I will show that in a second, and it's publicly available. You can go on that link and just play around with it. It's a different paradigm of how engineering is done. More relevant for now, on the prototype side of things, but also something that will expand across the whole life cycle. We'll also have some examples on manufacturing and other topics. But in this case, large geometry models, in this case, trained on 25 million geometries, really at the size of a GPT-1, trained on all sorts of geometries. You see automotive examples here, about 150,000, but really trained on all sorts of geometry, which again helps you to explore free shape geometry optimization, for example. But also relevant for a couple of manufacturing and operations examples. Then on the right side, we going to what we call a latent space. So you can encode and decode all these models into a sort of, you see as a common parameterization. The AI comes up with something you don't need to parameterize, but it still sort of defines the geometry itself. And you can always go back from this latent space into the geometric space. What's interesting here is that we've got a second model, which we call the large physics model, which is a pre-trained model that can, learns the physics itself, can predict the physics. In this case, and in the next case, I will show the demo, is aerodynamics and structural analysis. Of course, if you want to do more physics than that, you can do that as well. You can do that through fine-tuning or create another AI model, depending on, the architectural needs and things like that, and how complex the application is. Let's get into the interesting bit, I think. Show a little bit of examples how this could look like. And again, this is, let me move on, an example on aerospace, in this case, drone design. So where we're starting here is, and again, this is publicly available, have a look after. We start with a prompt. We can tell it, look, we want a drone that flies from Brooklyn to Manhattan or whatever, with a certain payload and a certain speed. So what this process is doing now, instead of what's done today in physics, is that you have got different solvers. You've got different operators running these simulations. You've got a different person creating the geometry based on experience and that, and that's awesome, right? But often you don't have that, or you just want to explore things. This is what this tool is for. Again, very early stage. So what you can see on the left side is this is the aerodynamic predictions. On the right side, we've got the stress predictions or the structural predictions. In the middle, we even optimizing for internal structure. There's a lot more to come, but I think it's quite interesting, looking at multi-domain optimization across multiphysics. This is something in real time enabled by AI. And you can see all these dots are actually geometries that were validated. You can see all the different geometries the large geometry model did come up with. That might be something like at the moment that looks like a normal airliner, but you also got a flying wing. You've got all sorts of designs, really exploring the whole design space of anything that sort of flies, giving you a global optimum design in a couple minutes, and something then a design engineer can go from there and bring it into reality. In this case, even covering, this is a drone, is not like a commercial airliner. So something that can be printed using continuous carbon fiber, also something where we integrate with the printer directly, and where we can even predict the principal stress. So where's the main stress, in which direction? And we can then tell the printer how to lay the fiber to make the most effective and lightweight design in terms of manufacturing. So I think here, as soon as you are happy with the design, we can also do some tweaks. We can do some morphing and things like that. It's a great tool, by the way, again, to just play around, get an instant prediction again. You also have things like flight stability, which is quite interesting. We can even incorporate things like manufacturing constraints, process parameters, all sorts of stuff, operational things. These models run in real time, so you can even integrate them into control loops and things like that. But just to give you a bit of a feel, this is a bit of a new paradigm how we think these tooling should be used, leveraging the speed of the AI models, but also the design freedom through these new ways of generative geometry. At the same time, of course, you can still incorporate parametric CAD into these models. I'll speak a little bit about the platform and things like that. But of course, this geometry could come from a CATIA, from an NX, from a SolidWorks, from any sort of geometry. At the same time, of course, we integrate with all sorts of tools for CE and physics simulation. Another use case, please, anybody, Sean, please stop me if I'm taking too long. I can skip a little bit. But I think quite an interesting application as well is chip cooling in this case. So what we're doing here, this one is automotive, but you can think of that as well as data center cooling, for example, where we've got high dense chips. You probably see the announcement, NVIDIA just moved to water cooling. In this case, it's IGBT, so it's for power inverters, and these chips each running at a couple thousand watts. So we really need water cooling in a high thermal density, get that away from the chip. So what we're doing here, on the left side, you can see this is a standard design, which is called a pin design, something that is quite easily parameterized, quite easily done in CAD, and something that we pre-optimize using a normal process, Siemens heats or something else. What we do instead, what we can do instead is, and again, here you can see that. So we upload that design. In blue, you can see the chips. What's important is not only the minimum or the maximum temperature, but also the uniformity. So all the chips should stay at the same temperature. On the left side, you can see water going in. On the right side, you can see water going out. And what's, of course, the issue is that the water is hotter at the right side than it is on the other side. So there is something we need to do. There's something we can do with parametric CAD, but in this way, what we're doing is connecting our generative geometry. Now we're running an optimization. Again, maybe let me stop here briefly. On the left side, you can see this is really a complex problem. You're optimizing uniformity, temperature. You can also do that with weight and pressure drop. In this case, we constrained pressure drop here because you don't want a bigger pump. But there's a lot of things. So what we're doing here with, in these 30 seconds of optimization, we run through over 100,000 of geometries. This is something that is, of course, completely infeasible using a physics numerical process. And what's probably more interesting to you is then the geometry side of things. So now live, we can go explore this, what's called the Pareto front, so something that is ideal in terms of all the different parameters. And we can create this geometry. We can look on the right side. We've got our main KPIs. It's 5 degrees better in maximum temperature, which can be magnitudes better in lifetime, and a lot better in uniformity, about over 50% better. We now getting to our comparison mode. This is something composable for all the apps and all the applications, and always looks the same. And here we can see the difference. Maybe let me stop here. Quite interesting in terms of design and how different that looks like. And what's interesting here is, of course, that this is nothing, a human has parameterized or some sort of parametric card. This is also not, again, topology optimization or anything. This is, of course, way too fast. This is something the generative AI model came up with. And it's quite interesting as an engineer to look at all these designs and look at how they work. And we'll do that a bit later. But you can already see through the live prediction that these already have a much better thermal distribution, a lot less hotspots. And again, this was only done in a few minutes, clicking through different designs. At the same time, of course, as I said, we integrate with all the CAD software. It's fully manufacturable. In this case, it's extruded. There are things we can do in terms of constraints, making that sure. And then here we are also integrating with, in this case, Siemens SimSenX, which is the SaaS offering of Siemens, to run that design back through your trusted CAE software. We can also feed geometries back into CAD systems, into your PLM system, and so on, of course, and continue the process. And maybe what's interesting here is, and I really like this design here you saw earlier, what the AI does is bypassing some of that cold water and feeding it back onto the last chip. So this, again, is not something any human probably would have come up with, right? But this is the AI figuring that out based on 1,000 iterations and 10,000s of iterations. And it's quite interesting to look at all these different designs. They work quite differently and somehow they work. And this is really then about the engineer to pick the best one, the most suitable one, also the one that is probably easiest to manufacture, things like that. Again, some of that is baked into the optimization, but some of that is, of course, needs guidance from the human. Let me go to the last one very quickly. Of course, we can do the same in terms of manufacturing. Quite interesting here. This is an application of casting. All these simulations take a long time. It takes a long time, to build the geometry models for different feeder locations and things like that. So the simulation alone takes 2 days. Getting the model running takes about a week, doing all the geometric changes. What we have built is a bit, very similarly, a UI that can do the same in a fraction of a second. So where you can, change the geometry, change all the feeder locations and everything, and you get live inference of, porosity and things like that in real time, which really helps the manufacturing experts in the production line to do that and also optimize for porosity, for all, thermal deformation and things like that. Before even running the first prototype. And this is usually a very painful process. And this tool is leveraging the speed of the AI, the modeling itself, streamlining everything together to make this as seamless as possible and, reducing the scrap rate as well, going from 0 to this workflow to an optimum, actually, perfectly casted or well enough casted design in one step, and in a few weeks rather than months. And I hope this gives a bit of an overview across the different applications. Of course, there's a lot more. Theo will also show some. I think what's important here is to mention, for us, it's not just about building a platform that can train AI models and having another tool in your repertoire. It's really about how you stitch it all together. A lot of that, of course, is not only about speeding up the CAE, the simulation, but also how can you come up with geometry faster? How can you leverage the speed of these models? It's also about how can you prepare, training data for the AI. So here we've got something called Simulation Workbench, which stitches in directly with AI Workbench. The AI can retrain itself as needed, using automation on the simulation side of things. And then, of course, we've got engineering apps to make all these models consumable easily through the apps you have seen in a second. You don't even need to be an engineer to run these models. And all of that is part of the offering. And we think is key to have a holistic experience and making AI work for these sort of applications. Let me stop here. And let me stop sharing maybe for a sec. If you want to play around with Airplane, I've got a QR code here. Otherwise, I'll hand back to Sean, and I think we'll happy to answer any questions later. Thank you.
Excellent. Thank you so much for that, Nico. That was fascinating. And as you said, yes, we'll bring you back later for some questions and answers. Next up, I'd like to introduce Theo Allard, the CTO and co-founder of NeuroConcept, a leading technology company that places AI at the center of the product development process. Theo joins us today to explore the ways in which AI-driven design and simulation have shortened development cycles, uncovered new designs, and improved performance. Please welcome Theo Allard.
Thank you, Sean, for the introduction. Let me share my screen quickly. So here we're sharing. So yeah, good morning, good afternoon, everyone, depending on where you are in the world. Very excited to be here today to talk about how AI is reshaping product development and how we at NeuroConcept are contributing to that shift. Before we dive into the core topic, let me quickly introduce the company. So at NeuroConcept, we've been pioneers in bringing AI into engineering for the last 7 years, since 2018. Today, we're a team of 80 passionate engineers and AI experts, headquartered in Lausanne, Switzerland, with offices in Germany, the US, and partners all across Asia. We're working with about 100 companies and trusted by hundreds of the most advanced engineering departments around the world, spanning many different industries and disciplines. And our mission is to embed AI deep into existing engineering workflows, to create real-world impact and better products much faster. But this is a little bit too abstract. So what I'll do is I'll start very quickly with a concrete example, building on the progress of decades of digitalization in engineering. So Nico already gave another version of this history, and I'm sure many of you listening today have witnessed the already groundbreaking evolution of engineering since the 80s, when CAD revolutionized manual drafting. Then in the 2000s, CAE started replacing a lot of prototype validations, which culminated in the 2010s with converging into design of experiments, allowing already to explore hundreds of designs, with a drawback of requiring weeks of preparation and pretty advanced expertise. And so today, my deep conviction is that the advent of AI design copilots is opening a new era in engineering, because now we're talking about thousands of designs per day that can be autonomously generated, validated, analyzed, refined. And so it really builds and pushes the promises of what was previously brought by design of experiment. So let me illustrate that and start with a concrete example. So what are we looking at here? What you're seeing here is the SP80 kite boat, or soon to be the fastest sails craft ever conceived. This sailcraft is today flying across water at over 50 knots, so more than 100 kilometers per hour. But why SP80? SP80 because it's targeting to reach 80 knots, or over 140 kilometers per hour. At these speeds, the big challenge is that water starts behaving differently. This isn't just a sailboat that was optimized to go faster. It had to be totally reimagined. And the cornerstone of this concept is a very special hydrofoil that operates on reverse principles compared to traditional foils like America's Cup boats. It instead of lifting the boat above the water, it's anchoring and digging into the water to extract massive propulsion from the kite. So that's an interesting concept, but the reason I'm telling this story is because it's a tremendously complex design and engineering achievement. And with traditional tools, it would have been nearly impossible to put together such a concept. And so SP80 turned to an AI-powered process, and together with them, with NVIDIA and powered by our Omniverse integration, we created a virtual testbed for this vessel, a multi-physics AI simulation environment where hundreds of foil and hull configurations could be explored together in real time. So the idea is in this AI-powered reality, SP80 is not just analyzing designs one after another. They're racing them against each other, and virtual versions of the boats, each slightly different, are competing in silico for the actual world record. And engineers and designers can collaborate together, observe how each of these designs performs under different wind, sea, and steering conditions. So they really get to select the concept that maximizes, in the end, their chances of breaking the record while maintaining the necessary safety margin. So that's really what we mean by AI-powered engineering for the end user, for the team behind the concept. It's not just about simulating physics, but really about crafting carefully the performance of the concept through continuous iterations, real-time collaboration, and all of this in high fidelity. And so if we go one level deeper, and we look at this challenge of designing the foil, the real frontier that this project has to push was about mastering one of the most extreme fluid dynamics challenges in naval engineering, which is cavidation. So at the speed at 140 kilometers per hour, the problem is that the water begins to vaporize around the foil, creating bubbles that collapse violently and could break everything. It's a phenomenon that's incredibly complex to model with physics, of course, but even harder to control in your design. But thanks to the AI-powered simulation loop, the good thing is SP80 could explore such a large design space. It could explore non-intuitive concepts and converge on a unique ventilating foil profile. And so this profile didn't only avoid cavitation, it really managed to harness it with controlled ventilation to stabilize the performance and reduce drag at record-breaking speed. So here, AI didn't replace the physics, actually. It augmented the engineer's understanding of it and helped to reinvent completely the design process. So yeah, SP80 is quite a unique story of passion and commitment to reaching unmatched performance with a world-class team. But from my perspective, what excites me even more is that at the same time, we're leveraging the same technology, the same learnings to put the same algorithms at work at industrial scale. So from Formula One teams like Williams Racing to OEMs like Subaru or to large-scale Tier 1 suppliers like OP Mobility, we're closing the gap from peak performance to operational excellence. And today, AI is helping companies achieve better performance with the same human and compute performance, providing the same product quality with less development time and bringing more innovative products to the market with better processes. And so, of course, with our customers, what's the common piece of the story is our central AI platform for engineering. We have a very product-centric approach, providing software to our customers, really empowering them to take full ownership of their AI transformation. The idea is it integrates with your CAD and CAE tools as data sources. It ingests design, simulation data, but also IoT sensor data, wind tunnel data, everything you have about the development and operations of your products. It's cloud native, it's scalable, it's powered by leading cloud infrastructure to give you the scale you need to explore that many designs and use leading AI algorithms. It enables you to harness all the leading engineering AI technology from physics prediction, geometry generation, but also reinforcement learning, optimization. Of course, it's coming with a unique core of proprietary algorithms, but it's an open platform. It's really built on an open architecture to allow you to integrate third-party technology as well, leveraging external models, building your own models as well. It's a completely extensible product architecture. And so the idea is eventually to put these workflows quickly in the hands of the people who are part of the product development process. So to deploy this in your existing product development tools and interfaces. And our goal is really that AI in engineering doesn't stay a research tool and integrates seamlessly with your organization's engineering backbone. And maybe even more than that, what's really important is that this transformation is beyond the tools, about the people using these tools, and so potentially about you. We believe that the engineers of the future of our AI augmented engineers, and that's why we've trained last year more than 200 engineers into CAE data scientists as part of our bootcamps program, empowering engineers to upskill in ML and automation while capitalizing on their existing domain knowledge. For this year, actually, we're targeting already the double of that number. And so as a summary, AI is an impact multiplier for engineering, but more importantly, for you as an engineer, as a designer, it's a career accelerator. And today, my advice is, as an engineer, it's urgent to invest in your AI literacy to increase your impact and become more relevant than ever in a market that's changing really fast. And I'm sure you can notice that from all the news you see in the field every day, and the progress that is happening by the week, by the months. And now I'd like to maybe wrap up this presentation with a concrete industrial example. Taking the example of one of our automotive OEM customers who deployed an NC-powered process for external aerodynamics. And 18 months down the road, after launching this process, they managed to look back and assess a bit the impact of this process, which resulted in about 20 drag counts reduction in the designs created with AI assistance. Overall saving 20 days of engineering time per program in the aerodynamics department. And overall, this is estimated to account for 100 million euros savings across their fleet in avoided EV powertrain development costs and avoided CO2 penalties. And I like this example because it's a clear illustration of how better engineering unlocks better business, and that's really what matters in the end with this AI transformation. And really the philosophy they use to approach that is by not being entirely tech focused. So it's really about blending deep technology, so ML for physics, geometry generative models, different types of AI models that also help with pre-processing. So some of the examples you could see in Nico's presentation before as well, and orchestrating these capabilities as part of novel processes that really bring data fluency into the organization's processes and tools. So manipulating dashboards, apps, and putting that in the hands of the engineers to create tools that the end users, the engineers, and the designers love instead of black box algorithms. And ultimately, this results in increased maturity for the organization. So when we look back now, we see the significant progress made by this customer in terms of AI maturity, things that used to require overnight turnaround times and PDF reports for CAE analysis with manual intervention are now interactive and directly available from apps. In terms of processes, this had a tremendous impact. So before this transformation, aerodynamicists were consistently running behind the process and providing analysis while the designers were always more moving forward. And this better tooling allowed them to get back in sync, and the reduced turnaround times really allowed them to work hand in hand. So we're not only improving technology, but improving organization. And now simulations are orchestrated automatically through automation. So really making AI and traditional CAE tools work seamlessly together while engineers can focus on where their input really matter and collaborating with designers on more creative processes. So this customer is a great example of leading the way to what we envision as a really AI native engineering process. And aerodynamics is only one of the examples of the flagship workflows we provide as part of the ENC platform that are available off the shelf to get started tomorrow with an AI-powered design and engineering process. We also have other workflows for thermal management, quite similar in terms of application for cold plate optimization, similar to what Nico demoed before, as well as electric motor development. So electric motor development requires the exploration of many design spaces, and engineers typically don't have the time to explore novel concepts. So AI is really a game changer here to discover designs that humans would never have thought of, and save costs, make designs that are more sustainable with reduced rare earth usage. And in the end, this also results in improved performance within the time available for the development of a new product. And beyond product development, we see more and more usage of NeuraConcept across the whole life cycle of a product, from R&D early on all the way to operations down the line. We have customers using the platform to deploy AI models to monitor manufacturing operations, to create virtual sensors of what's happening within a large manufacturing plants. And Yeah, so my message is really that you don't have to choose just one angle, and AI offers you multiple levers to pull and to create impact across your organization. So my message is clear. Start today. Today is already the ideal would have been yesterday, but yeah, start today, rethinking engineering, and focus on improving your designs, improving your processes, and bring AI into them. Thank you, and yeah, I'll hand it back over to Sean, and happy to answer any questions you may have.
Excellent. Thanks so much for that, Theo. That was fantastic. As you said, stick around. We do have some questions if we can bring Nico back as well. Um, we've got a number of them here. As mentioned, we're going to try to get through as many as possible. I think we're going to start with a bit of an existential one here. I'll ask Nico. There are still concerns around the use of AI despite its application. Somebody wants to know, how do we know we can trust AI models?
Yeah, very good question. And I think can also answer for Theo here a little bit. Please also add, Theo. What we of course can do is what's called uncertainty quantification. So the AI model can tell you where it's uncertain and where it's not. Of course, this is a level of trust there. At the same time, we then can use that uncertainty quantification to retrain the model surgically. And this is then the time where, as a user, you don't even need to worry about it, because the model will just retrain itself as needed. You can also do automatic validation. If you kick off a large optimization run, AI-based, overnight, it will, you can just set it up in a way that it will run the 5 best designs through your CE process or through your trusted process. This is then the way to fully trust it. But that's a good question. And I think, yeah, that's also why it's important to couple the numerical side of things or the traditional side of things with the AI side. It's really, as also Theo said, it's coupling both together instead of just adding another tool around AI. It's both working seamlessly together.
Excellent. Theo, you were talking about multi-physics predictions. Somebody wants to know, what types of physics can neural concept AI models predict? And they also wonder if there are any limitations.
Yeah, very good question. So in the example I showed with the foil optimization, for example, we handle multi-physics with hydrodynamics as well as structure together. And actually, it's two different AI models that get coupled together during the optimization process. But we can handle, I mean, it's a purely data-driven process. So the model architectures are pretty agnostic to the physics. So we handle a wide diversity of physics. You've seen examples with e-motors where we predict electromagnetics. We also predict non-physical quantities like cost, or we've predicted manufacturing time on certain manufacturing lines. Basically, the models couple in a data-driven way the geometries of each design with quantities, physical or not, that are correlated to these designs. Then beyond that, the platform offers different modeling strategies, different AI modeling strategies, and helps you analyze your use case, analyze the data you have available, and choose the right modeling strategy for your problem, because they indeed have different. Each of them will have indeed different limitations. So there was also a question about the limitations. Different techniques. So here I won't go in the detail of each different modeling technique, but different techniques have different limitations. And it's not only about pure AI modeling, but also about hybrid modeling. So you've probably heard about physics-informed machine learning. Some of the modeling techniques available in the platform allow you to inject physics inject knowledge into the problem to reduce the amount of training data you have and better constrain the results to be physical.
Excellent. Thank you. Now, Nico, I'm going to assume this question is for you. It came in during your presentation. Somebody wants to know, does the optimization process itself involve AI models, or does it use another optimization algorithm, i.e. evolutionary algorithms?
Yeah. No, great question. And of course, we are inferencing the AI model. So it's using AI in the loop instead of, the numerical simulation. In terms of algorithms, it's, the standard algorithms you would use. Evolutionary, you mentioned, of course, you can use gradient descent, you can use Bayesian optimization. But yeah, it's really with the AI model in the loop, using all sorts of algorithms. Usually what we find, especially in high dimensional design spaces, you want to use an evolutionary algorithm, with gradients, you always, that sometimes leads you into some artificial local minima. And, you, of course, if you can do 1 million designs per day, it doesn't need to be that efficient, and you usually it's great with an evolutionary algorithm to just explore the full design space and then go from there. So yeah, hope that answers the question.
Excellent. We've got time for a couple more. This one is for either of you. Somebody wants to know, how large of a data set is required to train a model?
That's the the question. Yeah, I don't know, Nico. I can go first, and then
Go for
you
it.
can complement. I mean, it's the question most people ask early on, and that's totally understandable. I mean, you have a certain engineering process, you have a certain use case in mind. There's only that much data you have available, and you want to know what you can expect from an AI model. I mean, in general, the answer is it depends. I will tell you some use cases provide great results with a few tens of samples, a few tens of designs and simulation results. Some other cases will require hundreds or thousands of designs to be really useful. What really matters is for you to know what you're looking for. Be very clear about the conditions under which your AI algorithm will be useful. What's the right criteria for it to help you in your decision making or in making a better design? And then, I mean, the good news is the NC platform provides you with the tools to give you answers very quickly and to find the right use case or to generate the missing data to start getting value out of your use case.
Maybe one comment to add here. And I'm sorry, I can't give an explicit number on that. That's also one reason why we're looking into, training bigger models, what we call foundation models. There are use cases. If you look at the aerospace example where we've got a model, if you look into these sort of physics, you can go to what's called zero shot. So you can give the model something that is quite different to what the model has seen, but it can still give you good prediction. Again, that's still a level of a question of the accuracy you need, as Theo explained earlier. But you can go as low as 0 or 5, let's say, with these foundation models. On the other side, if you start from scratch, of course, as Theo said, to the 10th, low hundreds, I think, is usually a good thing for capturing a highly nonlinear phenomena, which we're dealing with in CFD, FEA, and so on.
Excellent. Thanks for that, guys. With respect for everybody's time, we're going to wrap up right here. So I'd like to thank everybody for attending today's webinar. We really hope that you found today's discussion useful. And thanks so much to both of you, PhysicsX's Nico Haag and Neuroconcept's Theo Allard. We really appreciate your insights today concerning AI-powered CAD. If you happen to miss any of today's discussion, not to worry, we've recorded the webinar and we'll let everyone know when the recording is available for viewing. That's it for Design Engineering Magazine and part 2 of our 3-part AI for Engineers webinar series. Be sure to join us for part 3 on June 25th when we explore AI-powered inspection. Until then, take care.